So, good afternoon, all of you. On behalf of Amity University, I'll welcome our distinguished speaker, Dr. Sanjeev Kumar from HBTU Kanpur, to day 5, session 7 of this international FDP come short term course. So, before I hand over the session to Dr. Sanjeev, I would like to introduce him to you all. Dr. Sanjeev Kumar is currently working as Associate Professor in the Department of Electrical Engineering, HBTU Kanpur. He is senior member of professional bodies like IEEE and IETE. He has received ME and PhD degree from Indian Institute of Technology, Roorkee. He has published many books with reputed publishers like Lambert Academic Publishing. He has published many papers with journals and conferences of good repute and high impact factor like IEEE, Springer, etc. He is a reviewer of reputed journals of Springer and Taylor and Francis. He has supervised around 10 MTech and currently 4 PhDs are in pipeline. His research interests include multi-level inverters, open and winding induction motor drive, high power converters, industrial electric drive, microprocessor controlled electric drives, and active power filters. So we welcome you, sir, on behalf of Amity University and organizing team of the event. And I hand over the session to you.
Thank you, Neha, for such a wonderful introduction. As this is International Faculty Development Program come short-term course on the topic current advances in electric and hybrid vehicle technology, opportunity and challenges. And my topic is EV charging system. As we know, all of us are talking about the clean power and all. And electric vehicle come in that category because in this we try to reduce the carbon footprint. The biggest problem associated with electric vehicle is how to charge the source of this electric vehicle, that is the battery. So today's talk is related to various type of charging system of electric vehicles. My presentation includes introduction to electric vehicle, method of charging, modes and level of charging, conductive charging system in EVs, charger topology, and some simulation study I'll demonstrate, then conclusions. Right. As I told you already that why we prefer electric vehicle, because they are environment friendly, less running costs, less noise pollution, less maintenance cost, and reduction in carbon footprint. That is why we go for electric vehicle. If we talk about the type of electric vehicle, there are majorly classified in the 4 categories. The first one is hybrid electric vehicle. Second one is plug-in hybrid electric vehicle. The third one is mild hybrid electric vehicle. And fourth one is battery electric vehicle. In case of hybrid electric vehicle, there are 2 power drives. One is conventional IC engine and another one is electric motor with a larger battery. No need to plug in a hybrid electric vehicle because they charges via the regenerative braking action by the vehicle itself. If we talk about the second category, which is the plug-in hybrid electric vehicle, it is similar to hybrid electric vehicle. It also has an IC engine and electric motor with battery system, but it also has an additional charging port, which was not present in the hybrid electric vehicle. Hence, IC engine is used only when battery gets depleted. Right? Now, a mild hybrid electric vehicle, if we talk about this, it uses somewhere around 48-volt EV batteries and electric motor to increase the efficiency of the IC. Even when the IC is switched off, the electric motor can power non-essential features such as air conditioning, etc. And if we talk about the last category, that is the battery electric vehicle, in this type of vehicle, there is no as such IC engine. Only the car or vehicle is powered by the electric vehicle only. It has one or more electric motor, and they are powered by the large onboard battery. Right. So, com- component of electric vehicles are, I mainly talk about the electric vehicle, not hybrid. Hardcore electrical, the motor driven by electrical power, right? The battery is the first and more very much important component of the electric vehicle because it is the heart of the electric vehicle. It provides the power to run the motor. The second component is the power electronics component, of course, which are used with like converter, which is used to charge the battery. And I'll tell you there are several type of charging board and components related to the charging of electric battery. Then electric motor drive system and the bidirectional charger. Bidirectional charger where you can charge the battery using the charger and you can take the power from the battery itself. That is why it is called the bidirectional chargers. If we talk about the lead acid battery, there are two type of lead acid battery and lithium ion battery. And these are the specification of battery which you can get from any of the Google source or from any standard journal, right? If we talk about the component of the electric vehicle, these are the AC-DC converter, which are known as the rectifier. It is used for grid to vehicle, means whenever you want to charge your battery of the vehicle, then AC-DC converters are used. In this case, you take the power from the grid and fed to the battery system. Correct. And second is DC to AC inverter. It is used in bi-directional of charging, means when vehicle to grid. Whenever, for example, your vehicle is charged and you are not going to use this vehicle for more than a certain period, then you want to drain the battery by taking power from the battery to the supply system, or you can use it somewhere else to lightning equipment or somewhere else. Because if you don't discharge the battery, it assumes that its minimum level is 40. For example, you keep on discharging the battery up to 46 and then you charge the battery, then it will assume that the lower level is 46. That is the harmful for the battery health. So we have to drain the battery at least 8 to 10%, then only we charge, and we should not charge up to 100%. Right. And that is the different criteria associated with the charging of the battery, which you can study from any of the source. Now let's say DC-DC converter. It is used because you have to run a motor, and the motor speed has to be variable. So it means that the supply given to the motor has to be varied. For that purpose, DC-DC converter, which are of course the choppers, are used. Right? So for in general, it is seen that for cars, the battery voltage should be that 12 volt, and for buses it is 24. Then electric motor system, the commonly used is the induction motor, the permanent magnet synchronous motor, and direct current motor, and switch reluctance motors are also used. Right. And one of the very interesting configuration of induction motor for electric vehicle is open and winding induction motor. In this, what we do, we just open the neutral point of the induction motor and we fed the both side of the winding by the separate inverter. It will give you the performance corresponding to the multi-level inverter. For example, if we run the normal three-phase induction motor by two sides, uh, two level inverter, then it will give you the performance equivalent to three level inverter. That is the advantage of open induction motor. And that is electric motor with permanent magnet give the highest power and torque density. Traction motor in hybrid or electric cars will be a power rating larger than 10 kW. Right? And DC motor and induction motors are expensive, so we also think about the permanent magnet machine are more expensive depending upon the magnet cost. So all this constraint associated with different type of motor, depending upon the amount you can invest and the performance which you want, you can select a proper motor for the electric bike. Now we talk about the charger. It is classified in the two types. One is off-board and other one is the on-board charger. Off-board chargers can be placed at the charging station, like your you go and get the fuel for your normal electric vehicle. You simply go to the charging station and your vehicle will be charged. There are also certain scheme for this charging station, means one can go and replace the battery immediately, or you spend the time for 1 to 2 hours for charging the battery. So there are different type of schemes are available, and another type is that the charging vehicle. It means there are the vehicle which are having the supply system and the charge battery. You can just call them; they will come and replace your battery. Something like that. These are the various methods for charging. As Dr. Neha told me that the only 1 hour is allotted to me, so I have to wind up all these things. So these are very normal, I mean, simple things. So I am skipping all this. Right. Now let us come to the architecture of EVs. Here you can see there is a DC bus and there is a grid. From here, this grid, you are taking power from AC into DC. Now the power is in the form of DC, and this DC is feeding back to the electric vehicle, which is of course the battery of your electric vehicle. So you are taking the power from the grid. It could be non-conventional source like PV base. If you are working in the field of electric vehicle, you heard that Tesla has launched that the roof is of PV cell base. So your vehicle is automatically get charged while it is running from the solar energy. So PV is installed on the roof of the vehicle, and from PV cell battery get charged. And the third is the battery energy storage system. Battery energy storage system, there are battery which take the which is giving supply to the this DC bus, and from this DC bus your batteries get charged. Your batteries get charged at the same time. This battery energy storage system also getting power from this DC bus to charge itself. It could be via grid or it could be from the PV cell. Correct. So that is why here you can see it is the bi-direction. It is the bi-direction. There is in other two topology, it is the unidirectional. Right. So the method involves the replacement of discharge or depleted battery with a fresh new one. Instead of charging the old dead one, its advantage are hassle-free recharging, very time efficient, renewable energy resources can be integrated easily, can perform bulk bi-directional power flow with the grid. Right? Now, typical BSS system is like this. From transformer, of course, distribution transformer, power is converted from AC to DC, then it is go to the charger, then go to the battery pack. Right? And there are several this type of charger are connected and they are giving to the EV battery storage places. And the moment vehicle come, you simply swapping the equipment, means you are changing the battery. So without waiting, there is no waiting time like your fuel. When you go for refueling your fuel tank, you just go and then the refueling can be done within 1 or 2, 3 minutes. So simply in that way that the electric vehicle, if you run the electric vehicle, then battery can be replaced at the station itself. So the main challenges of implementing of this BSS is the different manufacturers are having their own compatibility. The possibility of getting battery with the same condition is different. right? Like Tesla is it's another company, Mercedes is another company, Maruti is another company, Tata is another company. They are using different batteries and all. So it is one of the constraints. Driving behavior will affect the swapping batteries having less state of health. Other is the feasibility. This is very big challenge for battery cell to design the battery in such a way that can easily be exchanged and be compatible. Means it can be exchanged at any battery swapping station. So that is the another design constraint should be considered. Now, if we talk about the infrastructure would be very complex and very expensive as I compare the other charging strategy. Each charging station will demand a huge power from the grid because so many number of battery are the charged simultaneously. So each car would be using two batteries at a time. One would be at a charging station and other inside the car. Then only you can do this. Right? Battery ownership. Now, this is another, the techno commercial constraint. In fact, rather than the techno, it is the commercial constraint. Either the vehicle owner should purchase two battery, which is to be exchanged alternatively, or does not own the battery, means all burden go on the charging station. We should think about this. Who will bear the cost of this extra battery? Right? Now, if we talk about the inductive charging, you can see there is a transmitter and receiver, and by the using the magnetic coil, your charging of the battery can be carried out. And now, I'm not going in detail of this. This is another scheme that is very dynamic in nature from vehicle to vehicle. You can see that this is the charge vehicle and this is the use. You can see the battery is drained, another charger vehicle came, and by using the inductive nature, the battery is get charged from charger vehicle to user vehicle. Right? So this is the another way of charging the battery. Now we talk about the modes and level of the charging. There are bifurcated into different levels depending upon the voltage and current rating. For example, if we talk about the level 1 charging, it is the slowest method and it uses standard 120 volt and 15 ampere single phase grounded. Right? In this case, no additional infrastructure is necessary. And if we talk about the cost, it is cost approximately 500 to $880. If we go for level 2 charging, it offers 208 volt or somewhere 240 volt, and it can go up to 80 ampere and 19 to 19.2 kilowatt. Right? And it can charge a typical electric vehicle overnight. Right? So fast charging time and standardized vehicle to charger connection, and cost is approximately $2,150. 2,150. And if we talk about the commercial fast charger, it operates at 480 volt or higher three-phase circuit, and cost is between 30,000 to 1,60,000, depending upon the performance and various parameters. And it can be means it could be shopping center, it could be hotel, or restaurant, because the charging time is very less. So you can go for shopping and meanwhile you're working at charge. So that is the means advantage of this fast charging. And modes of charging, there are several standards for charging. One is IEEE 61851-1 define 4 modes of charging. That mode 1 is the standard socket output. That is the domestic installation, means you can install at your home as well. Correct? And you can charge from a single phase supply. Another mode is standard socket outlet with an AC EV supply equipment. It is also domestic type charger. And the third mode is AC equipment permanently connected on AC supply network. Means charger is connected at the AC supply and you have to put your vehicle there. And the last one is the DC EV supply means like battery swapping or the means motorized electric vehicle charger. That is the case, right? In case of mode 1, only 2.3 kilowatt up to 22.3 kilowatt. You can see a car is there and you have to just give the a single phase AC supply and it will get charged. Whenever that electric vehicle come, we think that it is like always car. No, it could be your scooty, it could be a cycle, or it could be means a small thing which can used as the electric vehicle, right? So these are the domestic socket. And if we talk about the mode 3, here the level is increased and it could be 3.7 kilowatt to 22 kilowatt. 22 kilowatt. Here, the charger and everything are installed at the station itself. And this is the fast charging station. You can see that CHAdeMO, CCS combo, all this come under this mode 4. That is 350 kilowatt up to 350 kilowatt DC. All right. So this I am skipping because I have to cover so many slides. This is a very important charging, high fast charging. So I would like to discuss that is the chat. This is the DC charging technology. It enables seamless communication between the car and the charger. Capable of feeding energy back into the electric grid. That means it is the bi-direction. Means you can take power from the grid and you can send back power to the CHAdeMO protocol. Describe all the necessary stuff which must be followed before, during, and after the charging oblique discharging operation. It delivers power in the range of 6 kilowatt to 200 kilowatt. The CHAdeMO fast charger generally aim to charge the EV and PHEV batteries up to 80% capacity within less than 30 minutes. So you can imagine how powerful charger protocol is this. The control and charging discharging operation, the charger and the vehicle exchange controller area network, which is known as CAN. Controller area network means CAN. Message containing the control and status information. It will tell what is the status of the battery. Here is the field when IoT comes in the electric vehicle, right? So that type of things could be considered here, right? So this is the pin layout of the CHAdeMO. You can see that is the CAN is high. All this information has to be sent. That is the this controller area network, whether it is low, it is high, or so on and so. Right. So this is the here this all you can see Raspberry Pi can to seal can see. It is used for changing the information whether the charging station is available, how much charging time, and all those things are there. Battery management system means what is the status of battery, what is the state of charge. All these things can has to be provided between the CAN and the user. Right? So uh, this is the classification of bidirectional charger. You can see it can be classified into single stage or two stage charger. If we talk about the single stage, it could be single phase as well as three phase. If it is a single phase, ranging could be 0 to 7 kilowatt. Zero means, I mean, of course, there is no use of 7 kilowatt. The range is the maximum 7 kilowatt. And if we talk about the three phase, it could be 7 to 22 kilowatt. Now, level 1, 2, 3, and all this level and charging level I have already told you in the previous slides. So this is the basic architecture of two-stage charger. Why we call it two-stage charger? You can see that first it convert into AC power into DC, then from DC to DC. DC to DC means depending upon the voltage level of the battery. that DC level has to be changed. Means if it is a 24 volt or it is a 12 volt, so that level has to be achieved. This is the topology of integrated onboard battery charger. Means it is available in the vehicle itself, and you can just plug and play. Right, you have to supply the AC, and your battery get charged. The charger itself, it is the onboard charger. It is available in the vehicle itself. Right. So this is the single stage. You can see that AC voltage is converted into battery compatible DC voltage. Battery compatible DC voltage that is converted. And this is the three-phase single three-phase single stage OBC. You can see uh, what we are doing, that is AC is first converted into DC, then DC is converted into AC. Why we do this? We do this just to reduce the size of transformer. We are The supply is available at 50 hertz. If we convert it into DC, the size of the transformer has to be large. So what we do, we simply convert this AC into DC and generate a high frequency AC, very high frequency. So the size of the transformer is reduced. Corresponding weight volume cost is also reduced. And this is the DAB based matrix converter. Here you can see it is the single. There it is a three-phase charger, and the matrix converters is used for this. Dr. Neha is having experience. I remember her PhD topic was the somewhat related to matrix converter. Right. This is one simulation study which I would like to demonstrate you. Here you can see charger is it is bi-directional charger. Means this is the grid, and this grid charge this battery, and this battery run the your this electric vehicle. And when this battery is not in use, or we want to take the power fed back to the supply system, this battery is getting discharged by taking the power from battery to the grid. So it is the bi-directional EV charger. And this is the control strategy. If you, I have given the reference paper. So depending upon the paper and some our input, we have developed the control strategy and all. And this is the result. You can see the state of charge. It is changing from somewhere around 10% to 11.1% within 20 seconds. Right? So the increase is around 1.1 volt. Increase in charge is around 1.1 volt within 20 seconds. So you can imagine how fast charger it is. And this battery voltage, you can see it is almost constant. It is almost constant once it is charged. And this is the current of battery. You can see the current is negative, and it has to be negative because the charger is supplying power to the battery, and current is taking by the battery. That is why it is negative. Battery is not supplying the current. Battery is not supplying the current. That is why it is like this. And if you see the output of AC/DC converter, it is almost constant. It is almost constant after the 5 seconds. So it is charged by this voltage. And this is the switch voltage of various switches which we have connected in this topology. Just a minute. These switches. I hope it is visible to you. Just a minute. This, these switches, these switches. So all the voltage and everything is measured and analyzed. Not only this, we have also, and this is the state of charge. State of charge, you can see, state of charge is means battery is decreasing. This is the percentage state of charge. You can see from 80% to 79.5, means almost 0.5%. 0.5% decay in 7 seconds. 0 to 7. So we have also cross-checked our battery by discharging this from taking power to the supply system. And this is the battery voltage. You can see as the this percentage of state of the charge is somewhere around 80. So this the battery voltages remain constant, which is somewhere around 42, which is somewhere around 40. And this is the correct. And these are the various voltage across the switches. These are the various voltage across the switches. I am just demonstrating these results so that those who want to do work in this particular field, I will also show you the some live model as well as demonstrate on the OPEL-RT system. So that Mr. Arun Yadav, you want to say something? You have raised your hand.
Yes, yes, sir. I have
Yes,
one
please.
query.
Please.
Previously, you showed that in case of SOC decrease, the voltage
Yes.
remains almost constant. Suppose
Yes,
it
yes.
is decreasing more than, sir, if it is more than 10%, then also voltage will remain constant or it will decrease.
No, 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 no. See, unless until your battery is not getting discharged, whenever there is a load,
Hmm.
right, it will discharge.
Correct,
And
sir.
whenever up to a certain point, if the state of charge is somewhere around, we have observed that state of charge is 30 to 40% in between, the battery voltage remain constant. After that, the output voltage of the battery decrease. This is the topology because uh, we have developed that control strategy in such a way that you might notice the very simple question. You might notice whenever we use a small cell and for our small torch or something like that, or the trimmer, you can notice initially that trimmer speed is very fast, but as your battery getting discharged somewhere around 50%, then the speed of the motor start decreasing. The same phenomena is applicable here. Even if we are discharging the battery intentionally, we want to drain the power to the grid system. We are not running any load on the battery. We are supplying this power, battery DC power, to the grid system. Right?
Yes, sir.
Okay. So I will also give you some idea about the OPEL-RT system. You might notice whenever you do simulation and run the simulation for 2 seconds. So Arun, I would like to discuss with you because at least you have listened and raised some queries. Uh, do you work on MATLAB?
Sir, here we don't work on MATLAB as of now.
Okay, no problem, dear. Actually, whenever we do on work on MATLAB, we might notice that if we run the simulation for 2 seconds, just for example, 2 seconds, 3 seconds, sometime it run less than 3 seconds, and sometime it take more than 3 seconds. Even depending upon the complexity, if you run a simulation for 10 seconds, it may take 15 minutes, 20 minutes, or even 1 hour or more than 1 hour. So why it is so? Because ultimately MATLAB has to calculate certain equation depending upon the complexity of the model and give the result. So it's all the calculation, and how much time it takes to calculate that values. It the simulation time is I mean, simulation speed, not the time. Simulation speed is depend on that. But this OpenRT system, it is the real-time simulation. Here, the sampling time go up to small as 1 nanosecond, right? And you can run your simulation as it is in real time. For example, if you run your simulation for 2 seconds and you can calculate from your stopwatch, it will exactly finish within 2 seconds. That is the beauty of this OpenRT system. So we have run this model on real-time simulation, and here you can see the state of charge of battery in real-time mode. That means all these results are taken on the DSO, and we have found the same result what we have got in the simulation. That exactly same. In fact, a little bit improvement is found in the real-time simulation uh, simulator on the result in result. And here is the voltage and current. You can see the current is negative, and it has to be because the battery is getting charged, and battery this voltage output voltage is almost constant. And these are the switches voltage for Q1, Q2, Q3, which are the switch used in the our topology. So this is that one. These are the various uh, switching voltage at step down mode, and these are the voltage across the inductor. You can see in half of the cycle inductor get charged, and half of the cycle it is get discharged. And this is the current of inductor L1 and L2. And this is the state of charge, decreasing state of charge, discharging mode. You can notice from higher to lower level, charging is going down. And these are the discharging mode of current. You can again notice that ILV is now positive. It is now positive because battery is supplying power to the grid. Battery is supplying power to the grid, and these are the various switching voltages. These are the switch voltage across the switches. So all this thing we can examine in the real time simulator in the real world. So all these studies we have carried out, and these are the references which we have used to carried out this simulation study and all. And I'll also show you the MATLAB model. But as far as this presentation is concerned, this is end of this presentation. If you have any doubt, you can ask. And these are my email ID. You can send me mail if in future we wish you wish we can jointly do something, or I can be helpful to you in any aspect. Then you can talk to me. And this is the my YouTube channel. You can also go through this. There are several simulation model and all those things are given, so you can subscribe this and get benefited. If you wish, you can uh, do this. I'll show you. There are some lectures which I have taken at NIT. This MATLAB simulation of open and winding induction motor, the detailed study, and this open and winding induction motors are used in the electric vehicle as well. So you can see that the detailed description on the MATLAB based simulation model. This I have delivered at NIT, and it is of 2 hours 24 minutes. Right, to that you can take it. All these review of AC/DC converter and their MATLAB simulation. It is of marathon lecture of 4 hours 57 minutes 6 seconds. That also you can see if you wish. So all those things you can see, right? So this I have taken. So all this detailed study of AC/DC converter and everything you can find in this lecture. And in fact, how to develop MATLAB model, how to analyze the TSD, and everything is given in this. Right? So you can take the reference from here itself. Now, if you have any doubt, you can ask. And if you don't have any doubt, we can go for demonstration of MATLAB model. Yes, please.
So, dear participants, session is open for questions. If you have any query, you can go for.
And within 5 minutes, you can ask your doubt, so that after showing that MATLAB model, again you can ask your query. But since you have just seen your PPT, so if you have any doubt, you can ask.
If you don't have any query, then sir can
Of course,
go
we
for
can go for
demonstration of OpenRT results.
definitely. So Neha, should I proceed?
Yes, sir. I think they don't have any query. Sometimes
Okay.
they go through the recordings and study. Then they have
Fine.
query. They can connect with you.
Fine, and absolutely. So I'll show you one very simple model, which we have developed for just to develop for our BTech UG student to check the performance of single phase AC/DC rectifier. I'll show you what exactly it is. I hope my screen is visible, Neha. Dr. Neha?
Yes, sir. Yes, sir. It's visible.
Okay, fine. See, this is the rectifier model. You can see there are four switch. We already, it's very simple. Single phase AC supply is there, and this T1 and T4 is on during the positive cycle. T3 and T2 are on during the negative cycle, and the output voltage is measured across the RL type of load. What we did here, we have taken this output on our OpenRT system. So there are analog output module where we have connected this output. One is the input voltage, other one is the output voltage, and this is the last one, which is the load current. So all these three output we have connected our OpenRT analog output. And to trigger this rectifier in the real-time mode. Real-time mode means whenever you want to change the firing angle, if you notice, if you do work on the MATLAB, once you fix the firing angle, it is difficult to change the firing angle for during running time. But OpenRT give you the facility to change the firing angle during the running time. How it is could be done? It is thus simply cosine firing scheme is used. I have measured the input voltage and reduced by 25 times. It means input voltage is somewhere around 250. So I divide it by 25. So input voltage is come out to 10 volt. Now I have applied the this transportation delay of 0.05. 0.05 is corresponding to 5 milliseconds. If the cycle is 20 millisecond and it is 5 millisecond, then it will convert your sine wave into cosine. Why we use cosine firing scheme? Because that output voltage of the rectifier is twice Vm upon pi cos of alpha, means output voltage is proportional to cosine of firing angle. That is why we have converted the sine wave into cosine wave. and for T1, T2 positive and T3, T4 negative cycle is used. So we have invert this wave. And once zero crossing, sine wave is crossed from zero, then the for positive it will give you plus, and invert of that is given to the out 2. Out 2 means T3 and T4. That is why it is that. And reference signal, and this reference signal LN1 in 1 is given through this OPCOM block. This OPCOM block, whenever any external signal you are receiving to the model, it has to be processed through the OPCOM block. That is why it is used. And the entire system is divided into two groups. One is SM master and other one is SC console. So system master and system console are the two blocks. This console is available to the user. This console is available to the user. You can see this out. This out is basically fed back to the input. Means whenever you change this gain, your firing angle is changed. Your firing angle is changed. So that is how we have developed this model in real-time mode. And once it is developed, we have mod uh, simulate in the real-time mode. Once it is integrated with this RT simulator, you have to first build. In build, what it does, it will generate the C code and all and burn into its Spartan board. So that the code which is running in the real time, that is sent to this real time simulator. I'll show you. I hope this simulator is visible to you. This is the simulator. This one is the real time simulator. And here in DSO, you can, I hope my DSOs are visible to you. Here we see the output voltage, input voltage, and every. Now once it is bold, it should be load. Just a minute. Just some technical problems is coming. Just wait, let me restart. Just give me a second. This is the RT lab platform. Now just build. I hope DSO as well as my screen is visible to you. So from camera you can see the scope, DSO, and from screen you can see how this model is developed on real time. Now I hope you can see my scope is visible to you,
Yes, sir.
this DSO. So you can see at present the firing angle is 90. Firing angle is 90. Yellow one is the output and green one is the input. Green one is the input. Now easily you can see that firing angle is 90. Now I am going to change the firing angle. I am going to change the firing angle. You can see the screen as well as the DSO output. Let me run. You can see now the firing angle is somewhere around 45 degree. Now it is 0 degree. It is 0 degree. I should change the right. You can see this waveform which I am going to upscale just to remove this overlay. This is your green one is your input and this is your out. That you can see. Right, perfectly overlap. This negative cycle, this negative cycle is coming upside in the output, means it is reflected, because T3 T4 whenever T3 T4 conduct, that will give this output. Now I am again changing the firing angle. Let me run this. You can see once the moment I press the enter, immediately output voltage is changing. Immediately output voltage is changing. You just see, I have pressed 3, now I am just press enter. It is changed. So that is how it is changing. And you just see my screen. This is the, let me just, time range is 0.02. You just see, upper one is input and this is the output. This is the output and last is the output current. The output current, right? Because the inductive value is very less, that is why it is so. Now I'll do one experiment. Just change the Just change the value of inductor. Let it open in MATLAB. Just give me a second. This is your. You can see it was 10 ohm and inductor was 1 millihenry. Now I just change it 20 milli and save. Now what we have to do? Again we have to build. Again we have to build the model, load the model, and then run the model. Then we will see. You might notice that there is. I mean, after pi there is no waveform as such. Very small waveform was coming, negative cycle, because the value of inductor was quite low. Now I have increased 20 times from 1 millihenry to 20 millihenry. Now if I change the firing angle, you will notice that waveform will go up in the negative cycle as well. Why? Because the current flowing through the arrestor is not zero even after pi. That is why it is so. Just give me a second. Now let us update, and you just keep on watching the DSO. You just keep on watching the DSO window. You will find the moment I will run for the same firing angle, the here you can see. Here you can see. Now you can see the waveform. You can see the waveform. Right? Because the current become the continuous conduction. It become the continuous conduction, and it is let it come. Can see the effect of inductor, because you have increased the value of inductor is quite high. So that type of performance you can investigate from the Opel RT system in the real-time domain, right? As the time is already up just 1 o'clock, so I'll wind up my talk here. If you have any doubt, you can ask. Yes, please.
Yes,
Participant
participants.
session is open for questions. So if you don't have any questions, so we can end the session, and you can connect with Sir later. Sir has already given his ID and YouTube channel to you all.
Thank you very much, Sanjeev sir, for this wonderful talk. It was really mind-blowing, and definitely the participants will be benefited from your talk and the hands-on what you have demonstrated was really wonderful. So your talk will definitely motivate many more students and participants to research in this area, and they will connect with you in future. And definitely, sir, we are honored to have you on this platform today. And as we are having a IEEE student branch also over here, and we will love to hear from you in near future also, sir.
Yes, many sir. In fact, we are also having the IEEE student branch. In fact, power electronics chapter we have also opened recently. So it would be great if we jointly we organize something like that, because I mean crunch of manpower is always in the government. So that part you can manage, and rest we will manage. So jointly we can do
Definitely,
some
sir. It will be our pleasure to have you on that platform.
Of course, sir. Always.
Yeah, ma'am, can we have a group photograph with sir, with all the participants?
I request all the participants to kindly switch on their cameras for group photograph. And I request Sanjeev sir also to please switch on the camera. We want to have
No, dear, I have already turned on.
Okay, sir. So you are right now from your phone.
No. I am from the desktop itself. Actually, from my tablet as well as desktop. I have to log in. So if you wish, I can
No, sir. No,
turn it
sir.
on.
That those photos we have taken. We just want faces right now.
Astosh, just give it to tablet.
Sir, you are visible. You are visible. We can take.
Just give me a. Just give me.
Neha, I think
Neha, I
now
think
I am visible
now I am visible
in my both login.
in
Sir,
my
you
both
are visible. Now you are visible at two
Yes.
windows.
So that is
yes.
what I am saying.
So that is what
So
I
if
am
you
saying.
wish, so I can turn off
If you
video
wish,
from
so
one
I
of the
can turn off video one
login.
of the
It's perfect,
okay,
sir.
Wonderful.
login.
Yes.
Okay, wonderful.
We will have your multi-dimensional view, sir. Thank you, sir. Thank you very much to all the participants also.
Thank you. Thank you.
Thank you, guests and participants. Thank you so much.
ये किसी ने रिकॉर्डिंग बंद कर दी है क्या?
Yeah.